Right. Okay. So welcome back to lecture number 3 in our model Segmentation. Today we'll be studying color, grayscale and simple RGB color spaces. What is that? Color spaces in general and how we use the differences in color and differences in intensity to do some very crude and very simple segmentations. Right. Okay, so as for the outcomes, we'll be looking at image formats. And when I say looking, I'll be just providing the info on the slides. You can go home and check it out, right? It's not something that I have to go through. So we'll study the differences in a few color spaces. Now, there are a few, but in order for you to fully grasp why multiple color spaces exist, you should experiment with doing segmentations in different spaces. Right? So I can just tell you that there are multiple and show you how to do that experimentation. And finally, we will delve into the first algorithm that will let us extract information out of the images that we have. Right? So far, we have only extracted information. We had everyone. So when I say information, I mean things like how many people are there in an image, are there any people moving around, how can you detect moving objects, what is the predominant color, and what's the shape of the color, and what are some of the what's the orientation of certain objects. Those are the kind of very fundamental info that we can extract out of images. So in today's very simple stuff, we can extract that kind of information for a very limited amount of cases, right? But anyway, so this is the principle that we'll be applying throughout the entire module. Right? So the last 3 and 4 learning outcomes go hand in hand. Now there's a good reference book called the Handbook of Machine Vision. So it's not really a theory book. There's not that doesn't really go deep into mathematics. There is a small amount of mathematics there because we cannot call mathematics at all. But unlike the reference book given in the module description, this is very useful. And there are a few classic examples of classic implementations of machine and mostly 95% of the book deals with machine vision prior to the era of computational neural networks. Right? So everything, most of the stuff, I would say 95% of the stuff in this book was based on what was there before 2012. So useful in that sense. So it's something that you have to go through, and at multiple times, I will give you case studies and I'll point you to the chapters that you have to go through. So it's likely that I will give an exam question from what's in this book. Right? And if you want, there's a YouTube channel called OpenCV University. It's an official YouTube channel maintained by OpenCV. I can't remember OpenCV University or Learn OpenCV, whatever. So that's I'll find that link and send it to you. I forgot to attach it. So we'll start off with importing images into our workspace, and by import I mean so the images would already there be on the hard disk or in a camera. Importing by I mean acquiring them and loading them into the memory. So we'll have to deal with multiple formats. And how do these formats vary? They vary in the color depth they offer, whether the amount of channels that they offer, and the quality of the compression and so on. And some don't offer compression at all. So go through these things at home, right? It's quite straightforward, but one thing I want to know that I prefer to work with PNGs. So can you go over this table and tell me why I might prefer PNG or what might be the reason behind my preference? I prefer PNGs or see why that might be. Yeah, that's the main, one and only reason. It has compression, but that compression is lossless. So because it has compression, it will just simply reduce the size compared to kind of the raw image. due to the compression it reduces size, but that compression is lossless, therefore none of the information would be lost, right? So when we are dealing with images, we don't want to lose any information prior uh, to extracting the info. But anyways, now that being said, the differences due to the compression losses is kind of negligible, right? At least for 90% of the cases that we will study. But there are a few cases that where the compression loss might come into play, right? But for some reason, I kind of tend to use PNG. That's kind of the main reason. Okay. Uh, so I'll get back to this later on. Oh, no, I'll just start with it anyway. So I'll be studying or I'll be teaching you a few steps that we can go through. I would call them as a there are a few tools made available to us, image processing tools, we different stuff, but image processing tools made available to us, which we can use to extract information in the domain of segmentation. Right? So the list of tools that we'll be studying are these stuff. Studying today are these three: binary thresholding, color-based thresholding / segmentation, and background subtraction. In the future, we'll be studying the remaining feature-based segmentation and generic segmentation anyhow, right? So we'll be studying these three today. Uh, these three are unavoidable things that will pop up in every machine vision problem. Right? So as you can see, once we segment out an object, it would be easier for us to do localization. By localization, I mean figuring out the location and the orientation, right? So that's perhaps the most frequently occurring issue in terms of machine vision, and then tracking goes hand in hand with localization and property analysis and so on. They are usually property analysis comes handy in of, of product inspection in factories and so on. So anyways, once we segment out an object, we will be able to do these subsequent activities, right? So doing these activities is not the goal today, but first we need to extract some object out, or I would say narrow down our focus onto that particular object, and once we do that, we'll be able to do these things. So I hope you can figure out what segmentation is. If not, I'll give you a small example. Right? This is some image of the lake from, I think, if I remember properly, New Zealand or somewhere, so anyhow, right? So let's assume that we want to measure the amount of water or the area of the lake, or the color or the variation of the color of the lake with the season and so on. So it's impossible for us to do if we keep focusing on the whole image. That focused analysis on the lake cannot be done. Right? So the first thing that we need to do is we need to extract this area. You can see my mouse pointer. We need to extract this area out and kind of blacken out the rest, blacken out or whiten out the rest, so that our focus is on the lake only. Right? So that's segmentation, I think. So I gave you that example so that you know what segmentation is. If that hasn't been clear, right? So is it clear what segmentation is? That's kind of our goal. So segment means breaking down things into smaller pieces. In our case, we'll be breaking down images into kind of contiguous areas of interest. Okay, so so we'll be studying these three options. So the first is image thresholding, right? For image thresholding, or in other words, I would use this grayscale threshold, because this is possible only on grayscale images. Okay, so I'll start with an example. So I would need some points. So this would be a grayscale image going later black and white image. So carrying from previous stage grayscale image, you only have n by n matrix. And a single cell of the matrix will carry an intensity value. Right? So if the intensity value is 5, let's say 2 by 6, let's say each cell has 8 feet depth. So what would be the color of the pixel? So the intensity value is 2 by 6. White. And it's 0. Right, so in between values we have some shade of gray. So the points that we have over here, the white points we have intensity values closer to 2 by 6, and that backdrop we have intensity values closer to 0. Right. So let's say that so one study that we might want to carry out is analyze each coin one by one and take a look at what's on the face and check whether it's a 5. So these are US coins. So check whether it's a 5 cent, 2 cent, or a dollar or whatever. Check the value of the coin. So if you want to check the value of each and every one of these coins, first we should segment out the coins one by one. Right? So in order to do that, so how we first must remove the background and narrow down our focus on each and every one of these coins. Right. So the first thing you notice is this is a black and white image, and there's a deep contrast between the average intensity of the coin faces and the average intensity of the background. Right. So if you so is that clear? The coins are mostly white and the background is mostly black. Right? So there's a sharp difference between the colors, the background, and the coins, and the opposite of the background is called foreground. So the word foreground objects can also be used. So you will see that in the picture. Right? So when the difference in intensity between the foreground and between the background and foreground objects is very high, when the difference is high, you can be able to use this technique called image thresholding and multiple variants of it. So what they do is, so they have some value for the threshold, and this part in algorithm it goes to every single cell, checks whether the intensity of the cell is greater than threshold or higher than threshold, and based on that info, it classifies whether that pixel belongs to background or the foreground. This is what's described in the algorithm, but anyhow, so once we do that, so in this example, if I say the threshold, so the highest value of intensity is 256 and the lowest value is 0. If I say that the threshold value is 128, then upon applying this algorithm, it will kind of extract all the foreground objects into one class and the background objects into the other class. Okay, so let's dive into the demo to show you what really goes on behind the scenes. So I'm moving on to Python for this case. Hope it's visible. So if not, I can increase the brightness. Okay, so I'm not going to describe the code, but I'll just go through the comments in the code and so that show you know what has gone on. Right. So the first things first, we should know how to import these images into our RAM or read these images, right? So the first cell over here gives a, if you are not familiar with OpenCV and Python, so the first cell is a demo on how to read images, right? So you can read images from multiple sources, from cameras, from files, or from URLs, right? So for that particular purpose, this is a function that you can use regardless of the source, right? So I'm reading from a file stored on the hard disk, so this is what I use. So this is just a color image, so small demo on how to read images, and I'll share this file with you. So we'll be also when working with this algorithm, we'll have to display the results of subsequent processes. For that, I'm using PyPlot, right? Because in Jupyter notebooks, for some reason, OpenCV's imshow function does not work, and yeah. Okay. So now that I have imported this image into my workspace, I will I'll run a thresholding operation, right? And there are also multiple variants of these thresholding operations, right? So anyhow, since we just discussed what thresholding is, this is probably yeah, this is the output. If I use 127 or 128 as the threshold value, right? So if I run thresholding on this particular image with 127 as threshold, you might get something like this, right? And can anyone tell me what's the significance of 127 or 128?
It's the intermediate.
Yeah, it's intermediate values, right? So it's the intermediate value. So most of the time it might be a good threshold, most of the time, but depends on the case, right? Right. So thresholding by itself, it doesn't really do anything other than classify pixels to foreground to background. But what it does is it takes a grayscale image like this, what we have on the right over here, puts it through the algorithm, and it outputs something like this, which is a binary image. I would say that OYT. So in this particular output that we have over here, each pixel can only have two values, 1 or 0. Right? So it's 1 is right and 0 is right. So now some good segmentation has been done, and yeah, right, and now the value that we are going to use for thresholding can also have significant impact on any subsequent processes that we might have. So in this particular application, my goal might have been to analyze the values of the dominoes that we have on the table. Right. So there is a small issue with having threshold value of 127, right? And you can see that issue has been rectified with me choosing another threshold value, right? I hope that issue is clear to you. Do you see the issue with threshold 127? Right. And that you have negative. So we will see this later on. Right? So once we do thresholding and get that OY image or binary image, there is subsequent algorithm that we can control find contours and analyze contours, which we can focus on unconnected regions and do some analysis such as the area, the aspect ratio, the work circumference, and so on and so forth. Right? And if I want to run an analysis on individual dominoes, I can have connected regions like this. Now, this threshold value is affecting that, and that has been rectified with another threshold value. Right. So that is the basic or the very first image processing task that I have teaching you. So that's simple image threshold, or some also call it global thresholding as well. Okay, and then there's another thing called adaptive thresholding. Now in global thresholding was whether it's 127 or 80, there was only a single threshold value which we compare every single pixel with image elements. Right. And then there might be image cases where having a single value for the whole image might not get what we want. So for example, if we take an image like this, so let's say the ultimate goal is from Mozilla to request their own image. First, we have to do some image processing in order to remove the noise and kind of remove everything that's not the letter out of the image. So for that purpose, we will be using thresholding, and this is what we will get if you run global threshold we know what we studied in the previous slide. So if you use 127 or whatever kind of average you want, this is the result that you get because as you can see over here, on the left side of the image, the difference between the background and the letters is not that high, right? But over there on the right, the difference or the contrast between the foreground and the background and foreground objects is high. So as a result, what's over here would get properly thresholded, and you would see a very bad output over on the left hand side. Now, in cases like this, what should be done is called adaptive thresholding. So instead of a single threshold value for the whole image, in adaptive thresholding, what we do is so they will break down the image into multiple small windows, and then they will consider a small window as an image by itself. Right? And then in the window, they will figure out what the average intensity value for that window is, and do the thresholding based on that average value. And once that is done, so upon running adaptive thresholding, these kinds of proper segmentation into foreground and background objects is doable. Right. So adaptive thresholding is not a single bullet point thing. So based on the case, you have to decide whether you do go with global or adaptive threshold. So once I provide you the notebook and you go over it at home, you will see that use a different kind of function for adaptive threshold. Okay, so this is another example. So this is an image we start out with. Upon applying global thresholding, this is what we get. So not that good of a segmentation. So we have tried out multiple threshold values, and as we can see, it doesn't. We cannot really solve that with a threshold value alone. So we go with adaptive thresholding, and the result is proper segmentation. Okay, so a very simple thing. It's just what whether it's global or adaptive thresholding. What it does is it takes in a black and white or grayscale image and segments it out into background and foreground objects. Anyways, so some perhaps next lecture or the week after next will be doing an activity. So where we identify each and every one of these coins, and some of these coins will be fake. Right? So there are some coins which look like coins but are not coins at all. They don't have any markings on the face. And so we'll analyze the size of each individual coin. We'll figure out what the value is and kind of count the sum of the coins in the image. So this thresholding would be one step in that process, and I hope you can see what we might need that for. Right? So for the time being, by itself, these adaptive and global thresholding tools are not really that useful. Right, but we may move on to something that might have direct uses, as you can see over here. So it's color thresholding. So previously we ran operations on grayscale images. Now we from here onwards we run operations on color images. So in this technique we will be able to kind of say go to extract out only this particular region. Since you know that it has a grey color. If you know the RGB values for grey or the RGB values for grey now, then we can kind of extract out this image only and create some full mask. This is for the mask for the green region, and this is the extracted or the extracted green region. When combining this mask with the color image, we get the extracted. So the mask is a term that we should have familiar with. You will find it that will find that occurs for many of the subsequent lectures that you have. So the mask is essentially a binary image. Right? So ones and zeros. And we combine and align it with the mask, we can kind of extract out the unwanted regions and the wanted. So if you look at case number 2, color thresholding has been used to extract out perhaps the yellow colored uh, circles or whatever objects that we have on the table. Now there's this one more step that we can use if you want to extract simple information like how many yellow colored markings are there on the table. So from color segmentation only, we can obtain this particular mask or binary image, and then we can run uh, algorithms like find contours and count contours to figure out how many individual instances there are, how many individual foreground instances there are. So from here to here, we do color segmentation, and from afterwards we can do some contour analysis in order to count how many regions there are. It's not just for yellow color, for any kind of color, as long as it has a difference between itself and the background, there's a sharp difference between the foreground object's color and the background, you can segment it out. So coming back to our demonstration, so I read in the image, and essentially I have run a code so that I kind of isolate out or segment out the lake itself. Right. So I have created a mask. So don't focus on the third output right now. But the first output is essentially the raw image that I worked on. What we have in the middle is a mask for the lake main part. It's resultant highlight. When I figure out what the color for this lake is, and I run a color segmentation algorithm on the whole image by focusing on the color. But so this looks green, but anyways, it's not pure 02550 green. So as I told earlier, if you want to segment out the colors, one info that we should have is we should have the RGB values for the color inside the region that we want to segment out. For that purpose, there's a tool that we can use called PixSpy, and it's made available in ULMS, right? The external links. And when I hover the cursor over the region that I want to segment out, the RGB values will be given out here on the color changing on the box that changes colors, right? So that's a box here that kind of changes color based on where I'm hovering my mouse pointer, and when I bring it over here, it changes to green. But you will see that there's a range of RGB values that I need to encompass in my segmentation. And so I'll hover my mouse pointer over the whole region and kind of build up an image of what the maximum RGB value might be and what the lowest RGB value might be, RGB values might be within this region. So essentially, I am figuring out what the upper bound and the lower bound for the colors might be. Right? So this is what I have set. Right. So you will go home and you will see it for yourself as well. But upon running the mouse cursor throughout the whole lake region, I observed that the R value stays between 0 and 140. The green value stays between 158 and 245, and the red value stays between these two regions. Right. So we need to set up a lower bound for the color vector and the upper bound for the vector, and provide these combine these two bounds in order to do color based threshold, which is done using the in-range function. So So I'll go over the HSV in the next slide. Right? So anyways, now simply running your mouse pointer over this might not be sufficient, right? So that's a very ad hoc means of figuring out the lower bound and the upper bound. So what you can simply do is, after figuring out some truth bound, then you can figure out, then you can play around with these upper and lower bounds in order to kind of visually see what the best boundary is. Right? So this is a whole separate thing. I'll discuss it later. Right? So, anyways, once you do thresholding with the bounds that I have figured out, right? This is what we get, and I observe that this very small region of lake is not segmented the full bound that I have selected. Now, now the thing is, it's really difficult to segment. People have seen that it's really difficult to segment it out when the color space that we use is RGB, because RGB. So it's not a theory thing, but it's kind of an observation. RGB is not really helpful in figuring out these bounds and color segmentation. That brings us to the topic of color spaces, right? So now the concept of color spaces is kind of like a vector thing where the basis is. So if you know, you consider a 3D vector space. So any given point, so it is some point of interest to us. These are basis vectors. I, J, K are the basis vectors. Right? And you know that I, J, K are the only basis vectors. You know that, right? So you can kind of figure out some other independent vectors and use those two vectors as basis vectors and express this point using as a combination of these three as well. So essentially that's the method behind color spaces too. So color is a 3D space. So far, what we have represented every single color using three values R, G, and D values. Now, so the color space can also be represented using other three basic vectors, that those being hue, saturation, and value. So it's not something that I need to go. So these three have meaning, but anyways, it is really a practical thing. So people have figured out it's easier for us to figure out lower and upper bound for color regions if we represent color in this HSV space or any other spaces. Right? So HSV essentially is just another means of expressing color, right? And it kind of makes things easier. So anyway, so it's just like it's just like RGB but kind of different, used for expressing color. And then there's another tool I have given you called the colorizer, right? Third one from top. And here, so this is just a tool where we kind of okay, so as you can see, so there are a ton of color spaces anyhow. So I just focus on the first color space and the second. The first one I have is RGB, and the second one I have is actually the third one I have is HSV, right? So I think the output color would vary or it would change over here. So anyways, so as you can see, when I change my RGB values, the output color would change. But so this is kind of HSV is kind of a different basis, kind of a different set of basis vectors for the color space, and the same color expressed in these three RGB combinations can be represented using a different combinations. If I use the HSV as the basis vectors, right? So just two different techniques for us to represent the same thing. Right. So as you can see, if you take if you look at the HSV color space closely, if you focus in on the third parameter, in the third parameter the variation is very less, and that can be said the same for the second case as well, because in HSV the first parameter is what actually changes the color, right? The second parameter changes the brightness, and sorry, the third parameter changes the brightness, and the second one changes something called the saturation, which is also something that's kind of similar to brightness anyhow. So it's very, as you can see, so it's very easy to segment out color spaces, color objects. If you represent the color in HSV instead of RGB, right? So that's an observation that people have made. Uh, there's no need to go behind the mathematics theory and all that. So, anyways, it's just something that we'll observe, right? So, what I did was, so in my PixSpy, so unfortunately they only give the RGB values. But using colorizers, I kind of figured out what the HSV values for the RGB values are, and then I created the lower and upper bound for in lower and upper bounds in the HSV space. And then I ran color segmentation in the HSV space, and it seems it has done a better job of figuring out or segmenting out the whole portions of the list. So we have three distinct lake portions. It has been easier for me to segment out the lake since I am using HSV. So to tell you the truth, there's really a map called color thresholder in MATLAB. So that if you use that, it has a very good GUI and all. So that can be used to segment out these colors in a very interactive manner. So I just do it and figure out what the lower and upper bounds are. Right. Yeah. So that's color spaces. So it's just another method to represent color or the different set of basis vectors for a 3D space. Now there are multiple color spaces, not just RGB and HSV. There's LAB, YCR, CB, and CMYK, and so on. Right? So depending on your application, you might have to use different color space. Some cases RGB might be useful as well. So anyhow, once again, MATLAB has a really good tool in order to figure out which color space to use and how to figure out the bounds really easily. Right? So if I have time, I'll show you that at the end of the lecture. Right? So once again, this color-based segmentation and color spaces is not something that complicated. We just speaking in lay terms, we just run through the see the pixel and check the color value. If it falls within the lower and upper bound that we have specified, we call it a forward object. If it's out of that range, that's a backward object. Right, so over here, so this does thresholding in RGB space. This does thresholding in HSD space. And we have two masks. And I just wanted to show you that in most cases it might be easier to use HSV, mostly due to the fact that if you are willing to look at it deeply, it's easier to do things in HSV because there's a severe variation only in one parameter. The other two, they don't vary that much, right? If you take these two, they are mostly of the same color, it's different shades of the same color, unlike in RGB. So what I'll do is I'll open up MATLAB and it will take an hour or so to get it to, just to open it. And when it opens, I'll show you the differences between the color spaces. Right. So then we move on to something interesting called background subtraction, or the third week of I should have study background subtraction. So it's kind of a bit more complicated than what we are studying so far, but essentially mathematically simple. So the goal in background subtraction is to detect or segment out as covered object all objects that are moving. So in this we assume that the background doesn't change or background stays static, and if we make that assumption, anything that moves we classify as a programmed object. Now this is really simple to do, right? So if we need something like a video and an next we want to do it. We cannot do background subtraction or simple image. We need a reference. We need a fast reference. So let's say we have thread number one and thread number two. Thread number one and number two, and let's say there's some and thread number two. So thread number one, and the background is static for this one. So if man has moved another position, there will be certain cases where there are differences in pixels in frame number one and frame number two. In the background, so in regions like this, nothing can stay. So in both images, pixel would be the same. If I will compare number one and number two, the cases where nothing was there or nothing is there, uh, pixels would be the same with fast reference, so this would be background. And regions like this, are uh, because they are previously and now there would be some differences between the past records, the current past records. So that's the principle behind background subtraction. So what they really do is, so let's say there's some CCTV camera watching some region in some area, out of area, and our goal is to detect people walking around. And let's say this was done in 2002 or something that we didn't have CNN sensor. Structural is done by. So what we can do is, before a human comes into the frame, we can kind of get the CCTV camera able to make this for 1 minute or so, and we can kind of average out those images and build up a reference frame. Now, assume that this image was taken and there are no people coming. That would be a reference frame, or that would be the background frame. When there are no people around, that would be the background. So now let's say that it has gone on for some time and now people are coming in. And then if we kind of just simply mathematically subtract the background image from what we have now, there will be certain regions where the intensity is high, or there's a large difference between the background and what we have. So essentially, by drawing mathematically, this so this can be done from race images and other images too, right? Now I'm talking about a simple case, say 3 by 3 range of 9 pixels. So the higher analysis. So let's assume that this is the image that our camera has taken of the scene. For people have moved in, the camera has. In practical cases, the camera will have taken the images and average it out in order to build up what's called the background reference. Now let's say some very shiny ball is taken in a frame. So let's say our ball has an intensity of 2 by 5. Right? So now let's say ball is coming in. So now as soon as ball comes into this particular pixel's focus, this will change to 2 by 5. Right? Now the background subtraction algorithm will simply subtract subtract what we had previously from the current image. In that case, resultant that would be zeros all throughout all here and some value, let's say 20 or whatever some value, so the computer can figure out there's something going on in this particular view. And as soon as the ball moves into this pixel, this value of this pixel will change to whatever that has been here in the background, and now this will have some disparity value. So as the ball moves on, there the ball partially will have some disparity value instead of 0 or subtract. So that's the mathematical implementation of subtraction. Yeah, so so this is what we have on subtraction, and we do some simple threshold, which we say that anything 0 to 10 or so we classify as a forward object. So these all these zeros are below that very simple threshold, the zeros would be that one for that, and all these pixels which have higher value will be here binary. So we subtract the background frame from what we have now. We do a simple threshold in order to make a binary image. And then we get a mask for all the people or any object that is internal. Okay. So one of the very fastest tracking techniques that people have invented, very fast because it's just a simple mathematical subtraction and a thresholding operation. Right? So nothing can get faster than that. Yeah, and there are a few issues associated with this as well. So, can anyone tell me what the issues are if looking at the mass body? So, to zero. So, this is what we would actually get, right? I don't think this has been threshold, and this might not be a binary paper. This might be the output at this particular state of this after subtract. And as you can see over here, when cases where the D1 has come into play, so the pixels which actually belong to the D1, they will have a higher distraction. But in some cases, let's say pixels which fall into the shadow of the D1, they will have a lesser distraction. So there are noise removal techniques that you can use to remove out these particular shadows and all. Right? So once you apply those stuff, you should just focus in on the human one. So we will really use the background subtraction technique towards the end, and I will give you an assignment based on that as well. So I just right. So this is the video, and my goal is to measure the liquid level using visual means. So without any kind of liquid level measuring tools or whatever, I just used a camera in order to measure the liquid level. So a very simple thing. Right? So now can we discuss how we can use background subtraction in order to figure out the current liquid level? So discuss what I tell you very now. Right? So this is the background. Right? So around so I think it runs at 20 frames or somewhat, but there will be 20 frames where in those 20 frames this would be the only thing that we see. And if we kind of average out all those 20 frames, we will get the reference for the background. And from there onwards, so once the liquid starts coming into play, if we subtract the background from the current image, we will be able to isolate out the regions where something new has come into the frame, right? So unfortunately, we cannot discriminate between the foam and the liquid. But anyhow, so if we consider the foam to be part of the liquid as well, then this would be a very simple means of figuring out where the current liquid level is at. Right? So what you have to do is we just simply have to focus on the first few images, average them together from the reference, and then simply subtract that image from whatever we have left, and do some thresholding and yeah, show you. So do we have some demos to do? No. So I'll come to this after I do the demos. So anyhow, image simple grayscale thresholding, color based segmentation, and background subtraction are the three kind of fundamental tools that we can use to do crude segmentation. And this is what we can do after we segment out objects into foreground, after segment images into the background and foreground. These are all contours. You see kind of these puzzle pieces. If we draw them around the periphery of the puzzle pieces, we call that a contour. The periphery and whatever is inside. And there are contour analysis functions within OpenCV which we can use to evaluate these geometric properties of those contours. So this is just a very small list, but there are a ton of things that we can get from those analysis functions. Right. Contours. Contours. Right. The thing is, now this little thingy about contour analysis is something that we'll have to use even if we use CNNs and even the LLMs as well. Right. So most of the time, right, contour analysis comes towards the end of any machine vision workflow or whatever. Right. So this is something that we'll study in lecture number 3. But anyhow, even if we sort of even if we don't use color segmentation or background subtraction, and even if we use whatever neural network was discovered even yesterday, we still have to use some kind of contour analysis in order to gain this kind of very advanced info. Right. So this is the slide which provides us the segue into the next lecture, which is on filters and morphological operations. As you can see, nowadays grayscale thresholding, color thresholding, and background subtraction things, these are not ideal operations. Right? As you can see over here, right? So this is not perfectly segmented. Even in the puzzle piece, there are a few regions or a few pixels within the puzzle piece itself that are classified as background instead of foreground. So as a humans, we know that whatever is inside the puzzle piece is definitely cannot belong to the background, but the computer doesn't know that. It works on numbers. So what we'll study in lecture 4 would be techniques, filters, and morphological operations that we can use to kind of remove out these imperfections in the 3 techniques that we have studied today. So there's a slide that I should come back to, and I'll get back to this after I do the demonstrations. So anyways, what I had planned to teach is over for today. And there's a homework that you should do. You should read chapter 9.10.4 in Hornberg's handbook. Now I have provided you a link to Library Genesis. So if you click on this link and go to that site, you can download this book, right, for free, the PDF. And you should read this chapter. Just read it. Right? There's nothing else to do. There's no submission that you have to do. You just have to read it and be aware of it. So that's highly likely that I'll give you an question based on that alone. Now, the importance of this case study. So this was a case study taken from an application in German factory, I think, post or something. Right? So I had. So essentially, there were three pin types. They had to do some object recognition workflow or detect what kind of pin was coming into whatever into another pins. And the case study describes the number of obstacles that they had to overcome. And essentially, the solution they had implemented was so they had changed the different type of lighting, and essentially, this is the image that they have, this is the image that they obtain, right? And they implement the lighting, implement in process, and so on, so that what they get is a restful lighting itself, what they get is a grayscale image like this, and this is a image where there's a good contrast program and the back. And they do image simple and tutorial in this, and do getting they do analysis after that. And this is a real world machine vision solution implemented in Germany way back, just using what we have studied in last lecture and today's lecture. So read through that stuff, and then we'll move on to studying and doing a demonstration on a few things related to what we have studied today. Right. So these are not really industrial applications, but anyhow, good exercises for us in order to kind of implement what we have studied today. So I will focus in on these two and another one over here. So let's start with application number 4, figuring out the value and type of this playing card. And so the value, so it's obvious to us that's 10, right? So the type is whether it's a diamond, spade, club, heart, or whatever, and the color of the image, right? So that can be done just using what we have learned today, and it's implemented in the code. So we'll go over to check it out. But before we do that, shall we just discuss amongst ourselves what we can do? So let's start with figuring out the color of the whole card. So what can we do? So this can be done using what we studied in last week. So how can we figure out the color? So of course, background is white. Cards are either red or black. Cards are either red or black. So the first thing that we need to do is we need to differentiate whether it's red or black. So how do we do that? I am open to suggestions. So first thing that you should do is you should see the color image as a collection of 8 matrices. So the color image is actually 3 matrices. One matrix for the red intensities, one for the green intensities, and one for the blue intensities. So that's one way of looking at it. You can see it as a matrix where each cell has 3 elements. This is what the computer sees it as. Now, this is how the computer sees it. What can the computer do in order to figure out the color? So, what would be the ideal color for red in terms of RGB space? What would be the value?
Like around 2.5.
Yeah, white. Pure red 255 is 0. So, no green and no blue. For white, what would that be?
White. Coca.
So all are pure white. So that it will be 0. So if this is a pure white, so if this is simply white region, and if there are no, these objects aren't here, this is a pure white color box. If we average out the value, then what would that be? If we take the average out of the whole image, and find the average RGB value of the whole image. What is that? Right, so by averaging, I mean, so each pixel has three values. So we go over the pixels, sum up all the three values, and divide the sum for each channel by how many pixels there are. So if you do that averaging, what would be the final value that we get? It is a complete white box.
Completely right.
Yeah, 255, yeah, 255, 255, right? Not just 255. It's a color image still, but it's completely white. So MSN will have three values. It's a completely white box, but will have for every pixel is 255, 6, 256, 256. So if you average every single pixel, then you would get something like 256, 256, 256 as an average. So now if it's preordained, then what would that be? Definitely instead of this would be 0 and this would be closer to it. And it's a mixture of red and white. So it would have elements of white and it would be more skewed towards white picture. So if instead of red over here, red blocks over here, we have that. And what kind of skewness would that be? That would be closer to 0, not closer to 0 because the background is silver. So anyways, what I wanted to point out was the fact that so this figuring out the predominant color is what something that we can do simply by averaging out every single pixel in the image. Right. So yes, that. Yeah. So this is the cell where I have implemented that. So I read the image, right? So I read in the image. And another good thing about this is if you aren't clear what I do, what I have done, just select the code and hit explain over here, and Copilot will give you an explanation. Right? If you can figure it out, figure out what has happened. Okay, so the first two things both are related to reading in an image. First loads it into the RAM, and the second one, so there's really an issue with OpenCV's imprint function. It reads in an image in the BGR color format for historical reasons, I think. So we should convert that into from BGR to RGB. So that's what's being done over here, right? So that's also made clear in the documentation for the imprint function as well, right? So if you so we read in the image, and then I simply, in order to write this code, I simply wrote this comment. Right. So let's say I simply cut it out. If I don't know what to do, I give it some time in order to figure it out. Right. So have you observed that this is possible since you have installed Copilot? Copilot install කරලා නිකන් හිටියද මම එක්කෙනෙක් ඔයාලා අනිත් කට්ටිය install කරලා නිකන් හිටියද? Right. Right. So this is why I told you to download Copilot, right? So most of the stuff I have written here just using comments alone, right? So as you can see, if you can, so it's a bit there's an issue with the internet connection, but otherwise it will be very fast. So depending on so as soon as you write the comment and you hit enter, the code that needs to be written will pop up, right? So I find the average of the red, green, and blue values. So and I print it, and this is what we get, right? So now this is where we have to do another thing. So we should have an equivalent black color image as well, and we should average out the RGB values to the black color image too, right? And based on comparison of those two average values, we will set the threshold where we decide if it's greater than this. So this is red, if it's otherwise it's black. So the only evaluation that, or the only image processing that we have to do is a simple average, and you don't even need to know what function to use as well. I even still don't know what these things mean, but I know what goes on, but calling it essentially, I really haven't read the documentation and figured out what to input, and so just type in the average. Right, so that's how you would figure out whether it's red or black. You would average out the colors, and then you should have averaged out a 10 color, a black 10 diamond card as well in order to figure out what threshold might be. So, anyways, that's it. So now there are two things left, and that is to figure out the number, and the other is to figure out the type of card. So let's focus in on the number first. So I'll give you a hint. So now since we know that this is we can do color segmentation in order to extract out all the red color controls. So I'll do that, and subsequently let's see what we can do. Right. Of course, the next thing I do is I create a mask for the red color, and this is the upper bound and the lower bound. As you can see over here, it's very skewed towards the red. And then using this function, I do color segmentation and I plot everything side by side. So this is for another image, this is for 7, but anyhow. So this is what I would get, a binary mask after I do color based segmentation. Now all things that you see in white are the foreground objects which have been segmented out. But still we cannot read whether we don't have the facility to do OCR. Right? We still must find some other means of figuring out the number of objects and the type of card. Right? And then now do a small counting operation and tell me how many individual objects there are in this particular image. Consider this to be one. Don't consider this to be two individual cases. Just consider it to be one object. Same thing. Tell me how many objects there are. Okay. So how many objects would there be for a card with number 7? So if you notice the pattern, right? So in the card we will have this pattern card. If the card number is 7, we will have 7 patterns. And 2 more objects depicting the number, and 2 more objects are below number depicting the pattern. So then, I think just by counting how many individual objects there are, we are trying to figure out the number of the card. Right, so we know for a fact that if it's 11, the number of individual objects in the segment is 11, then we know that the value of the card is 7. The same is for 8, it's going to be 12. For 8, it's going to be 12, for 9 also is going to be 30. From 10 onwards, it's not actually going to be 14 because the segmentation is good. This would be related to so 56 is but it's okay because it's there onwards, just carry on that. So now we know just how to figure out the number of the card based on how many contours that we can find. So once we do the color based segmentation, I have plotted the original and the segmented object, and then I have run a contour extraction algorithm. Right, this is not a counter. So then I will count how many objects there are. Right, there are 11 contours over here. So we know for the fact that if there are 11 contours, then that means the card is number 7, right? So what else do we have left? And that is to figure out whether this is a spade, club, or whatever are those 4 things. Right. So that's a bit tricky, and for that purpose, you will have to do this contour geometry analysis. So you will have to compare the area, centroid, of the contour properties and aspect ratios. So, and before we do that, there's another observation that you need to make. Now, what are the largest, or what are the contours in the largest areas, and what are the contours in the smallest areas? So the contours in the middle, those have the largest area. The individual objects, this particular individual object, it will have the largest area of that these. So the thing is, I want to evaluate the aspect ratio of one of these things, and I need a way of figuring out whether I am analyzing the area of this particular object, this one, or one of these. Right? So that's why I need the observation that whatever these objects in the middle will have the highest area. Right? This is kind of generally true for all the other cards as well. You can go home and check it out for yourself. So for this particular reason, once I find the contours, right? Once I find the contours using find contours, and once I print out the number of contours, then that's why I kind of needed to sort it based on, I need to sort the list of contours based on the area. So then I know for a fact that the contour info of whatever's in the middle would be at the top, right? So then if I analyze it, then I know for a fact that if I take the contour object at the top of the list, then I am sure that I will be analyzing property of these of the 10 and the smaller plan. Right, so once I get hold of that contour object, it's a simple, there's a single line of code to be run there onwards in order to kind of extract out these information: area, centroid, contour, periphery, aspect ratio, and so aspect ratio. So this would have, so aspect ratio would be able to decipher between this like this. I'm not sure whether this has a high aspect ratio, but this has high and low aspect ratio. And yeah. And if you want to extract out all those information on the contour, to extract this information, then I simply wrote this single line of code, and Copilot did the rest for me. And this is kind of the information that you will get. So as you can see, the first 7 objects have the same thing. So I extracted area, perimeter, and aspect ratio. Now, of course, between the different types of cards, I don't know, there's something that looks like this. You can set it. Now, so you can kind of evaluate the areas of these four, evaluate the peripheries, evaluate the aspect ratios. I'm not sure about the aspect ratios, it might be the same. But anyways, this will definitely have a high area. So it has a take your time, right? So if you look at areas, territories, as not just only these three, but there are few that we have understand. Here, and you see that these four will have distinct areas and territories. So just need one parameter that you can use in order to make the differentiation on whether it's a diamond, the heart, state, or whatever. Right? So after this, after we extract this info, we can simply write an else if statement or a case which whatever. So case is not relevant fine, but anyways, we can simply write an if else statement in order to classify whether this is a diamond, spade, or whatever based on the area that it has. So the card manufacturers, they will also always ensure that the diamond size would be the same for every single card with a diamond in it. Right. So if you want to do that, go home and kind of add this if else statement, and you can maybe ask Copilot to do that for you. Right. So that's how you do that simple task. I don't know, maybe probably might be simple, but anyhow. Uh, right, and I think I have enough time in order to show you how to do color thresholding in multiple color spaces, and we might need that in order to do this first task, that is to detecting ripe blueberries. The ripe blueberries will have a blue color, and the unripe ones or the young blueberries will have a yellow color. So there are there are a few final year projects proposing similar stuff last year too and this year too as well. So you guys use what image? You train neural networks to do that for you. Okay, right? So that's one option that you can take. There is a new option that you can take. But in some cases, particularly in this one, so this is not something that you can apply anywhere. But in the case of blueberries, fortunately for us, the difference between ripe and young blueberries is in the color. I think it's not in the size, it's not in the texture, it's in the color. And so it's a matter of finding out the upper and lower bounds in order to segment out the right ones. So it's really easy to do in MATLAB, and I will just show you my workflow. I usually, but I almost every time I first do it using the color threshold app in order to figure out the bounds. Then I just copy the bounds over to Python to do it for. It's a hell of a headache to do use PixPy, color riser, and all those. So the first question that it will ask is to figure out the color space. So we can do segmentation in 4 spaces in the color threshold app. Right. So this is a really good visualization on the usefulness of different color spaces. Right. So color is a 3D space, and that's why it can be visualized using a cube like this. Right. So what I wanted to say is, it would be easier to kind of threshold out the color of our preference if it's more spread around, and it's kind of we want to segment out the blue color regions, and if the blue color regions is kind of separated out from the rest, it would be easier for us to segment it out. right? And I kind of see that in the LAB color space, all the blue pixels are kind of far away from the rest of the colors and kind of and would be easier to segment, right? So anyhow, let's go with RGB space and see it in action. Right. So this is what I previously did in Python by setting a lower and upper bound, right? So so anything beyond the lower bound would be removed, and that can be set for all the other colors. So anyhow, this is hell of an uneasy task to do, especially in RGB color space, right? So I would spend a ton of time wrangling with this in RGB. So I'll go over to LAB, and I think it would be quicker. Right. As you can see now, so it's not that spread out in LAB, right? So might be easier for us to figure out what the right ones must be. So I'm not going beyond this stage, but you saw how easy it was just to change the colors. Right? So there's no theoretical means of figuring out which color space is best for your application case. You need to first so that visualization for visualizations we saw at the beginning. Three D spaces were shown to us, right? So I knew for a fact that LAB would be easier because the blue colors were kind of they stood far away from the rest in the LAB visualization. So if you can see, I have kind of honed in on the blueberries at this point, and so these are the upper bounds and the lower bounds. So you just need to put them in vector if you were to use this in Python. So you have the 6 numbers that you need. That is what I do, right, in segmenting these things out. So I'll leave that as a task to you. If you have MATLAB, okay, you can figure it out. But I think at least one of you have MATLAB, you can figure out the 3 threshold values in MATLAB. Then others can do the segmentation stuff. It's a matter of simply wanted to do the segmentation, just change the name to the image and change these 6 values. That would be it. Right. So to localize the fish, I'll post this to you as a question. So assume that this is a video of a fish tank with a single fish name. So if you want to figure out the center of the fish group, what can we do? What are options that we have? So first, take a look at the image, observe it, observe the foreground, observe the background, and give me a few options on what I can do. So there are only 3 options that we study today. Think about them and think about so the picture and tell me what can we use. So localizing means I need the centroid, and it will also be great if I can kind of make the orientation of the fish as well. So anyhow, centroid and orientation is something that we can do with contour analysis once we segment out the fish first. So first we need to segment out the fish. So what can we do? So this is not a single image. This can also be video stream as well. And I'll ask the question: is the fish's skin color very different from the surroundings? the white and orange fish is different from the surroundings. So the color is very different from the surroundings, then of course you can use color segmentation. But there might be also there are black regions in the fish. There are black regions within the background clusters or might not be ideal. You can try it out and see, but anyhow I don't think that would be the case. Another question that I will pose to you: would the fish stay the same, or would the fish stay static in the fish bowl? Then you could move around. You have seen fish tanks; they move around, like droppers and move around over time. So the background would stay static. Now, because I have said the reason I have given you can someone say where I am ready in order to segment out the fish from the background. So we just have three options. Global adaptation is one. Short is one, and third is background subtract. So studying background subtract. Those are the things that we studied today. So the option left to us is for static background subtraction. First we need to point the camera to the background for some file and take the few images and analyze them out in order to figure out what the background is. Use it as a reference and from subsequent images we simply subtract by formula. If we subtract the background away, we will be able to get a contour for the fish. Right? We will be able to get a foreground object for the fish, and after we get that, then we would have to analyze these properties. So analyzing these properties is quite so behind the scenes it's quite difficult, but for us it's just find the contours using one function, and then once you find the contours it also does the analysis for you. So all these properties are within the contour. Alright, perhaps we read other areas. Right. Okay, so let's take a look at our liquid video. Liquid filling video. So this is an assignment. Also, this is visual assessment of the liquid level. This is something that we do for the whole sets. Anything that we do, but as we move on, we will see that today we have discussed a set of options that we can use. In the next and in 1 or 2 weeks time we will have another set of tools, so that will improve our accuracy of liquid evaluation, and in a few weeks time we'll have more set of tools, and even in the last week there would be another set of tools we can use to measure the liquid level. So you yourself will see a progression in you will be able to visualize a progression in machine vision as well. Right. So as we discussed, definitely background subtraction is something we can do if we want to extract out whatever's not the background and whatever's the background. Right. So today you will use background subtraction in order to segment out this particular part which is not the background. Right, and then you will measure the area or whatever. So you measure area is the easiest to measure, and using area measurement you will kind of come up with a number for the liquid level and plot it using a XY or whatever, using a 2D graph, and that's what I want as your next take home assignment. And I've given you some aid to get you started in it. Right. So this is a video. So InRead is not going to work in this case. There's a function we had used called video capture. So this will load the video from the hard disk into the RAM. And whenever you call the read function, so the video reader object will have a kind of a what do you call it, will maintain an index of the current frame that is read. And when you read a frame, it will move on to the next index, and when you call the read function next time, the next frame is what you read. So what I have provided to you for the moment is I have I have created the video capture object. I have read in the first frame, and then I have read the metadata in order to figure out how many frames there are. And then I have selected some random image or random frame index or some image down the line, and I have read that, compared both to converted both to grayscale, and then these two have done the background subtraction. So this is the mathematical subtraction, and this is the thresholding that I told you. So you remember, upon simple subtraction, you will get some number over here and do some thresholding after that in order to convert it into a binary. So that's what's coming in the threshold line. So everything after that is just plotting the outputs of subsequent stages, right? So this is the first image. So I haven't done averaging. I have just taken the first image as the background. Right? So just by looking at the video, it has stayed pretty static. So I assumed, made the reasonable assumption that the first image is the background and it doesn't vary. So this is the background. So this is the random frame or the 100th frame. This is what I get after I subtract the background from the current image and do thresholding. Now, as you can see, I think my threshold value was not ideal, right? So you will have to work on that, do some trial and error. So change. I'll change this to. I'll do it. See what happens. Right, anyhow, so at this stage we will not be able to gain a very accurate reading, right? But I want you to gain some reading, and in the subsequent lectures we'll improve it. And at the end of the lecture series or at the end of the module, we'll have a very accurate method of visually reading the liquid level. So what you have to do is, so this is just, I have just done it for a random frame. You have to do this for the whole series or the whole, how many frames? Let's see how many frames we have. So it's reading my mind. So you have to do it for the whole 239 images, because the first you use as the background, right? So you will have 239 data points. You have to do this particular thing for all 239, and you have to plot the liquid level as a 2D graph. And that has to be, not that, but the whole notebook has to be submitted as the take home assignment. If you want, you can check out, I have given links to do 2 YouTube videos as well. I'm not going to discuss those things now, but anyhow, this is something that we can do with the 3 techniques that we have discussed today, right? Not to the best extent, but to some extent, at least filtering out the lane markings can be done. And the lecture is not over yet. Yeah. Right. I said I'd come back to this slide, not to kind of focusing on these geometric properties, but rather there's something, but rather to focusing on this bounding box, right? Now let's assume that this is the grayscale image of this. I have the actual image. Right. Right. So this is the grayscale of which grayscale bracketing might be colors. Yeah. So let's say I want to detect, so I want to generate actions for the individual objects that are present in this image. So for every individual, we have studied image, we are cannot specify whether it is a camel or whether it is a pointing or passing out. But we have studied today, you can kind of generate the bounding box for these objects present, and you can drop out these bounding boxes and you can pass these on some subsequent classifier. I'll show you how to do that. So now my focus is on how to crop out these individual objects. So first things first, we need to segment them out. So going back to our three options, thresholding, color segmentation, or background subtraction. So background subtraction is definitely out. Color segmentation, I think simple thresholding would do, right? So I have tried out simple thresholding. So if you are not sure whether it might work or not, so go ahead and try it out, right? So I have opened the image. So it's a color one, but I converted into grayscale, and then I ran image thresholding. Right? If we don't, yeah, I think with the threshold as 200. So upon thresholding with the threshold as 200, this is what I get, right? So now upon running the find contours function, then I will be able to kind of get info on these contours, right? So I have the binary image, and then upon on a binary image I can run the find contours function, and this is a very clear binary image as well. Now upon running the find contours function, I will get access to the contour objects, and what I really need is the centroid and bounding box information, right? I'll need the bounding box information. So either in some cases, I need. So this is a bounding box. Right? Now over here, so some will provide the centroid location and the height and width of the bounding box. Some will provide the coordinates, xy coordinates of the upper left and the lower right corners. Some will provide the coordinates of the upper left corner and the height and width of the bounding box. If you are not sure, then you need to kind of go to OpenCV's documentation, or in other words, just ask an LLM, right? That's easier in these days. Right, so I think what OpenCV offers is the coordinates of this particular point and the height and width of the bounding. So I want to crop it out, crop this particular camel out. I don't know it's a camel, but I want to crop out this rectangular region containing all these volumes. So let's see how I have done that. So going back to the code, so where did I leave things? I think I left things here. I opened, converted to grayscale, thresholded, plotted things side by side, and then I need to find the contours. And I have also printed out how many contours there are. Right? This is to do some to check whether I am on the right track. Right? So I really don't need how many contours there are, but I still do these kind of things just to kind of not debugging, but rather to debug the algorithm, I would say, not the program itself. From then onwards, I have drawn the contours so that I will be able to kind of visualize the contours and subsequently also. So I have drawn multiple stuff. So whatever's in between, I have properly commented. So I have essentially I have drawn out different kinds of bounding boxes, different kinds of oriented bounding boxes, or the smaller street bounding boxes. I have drawn out the contours, sorry, the centroids, so on and so forth. Right? Up to this point, yeah, I have drawn out multiple things. But the interesting stuff comes from here onwards. Right? So this is a loop, and within this loop, for each contour, I figure out the x and y coordinates of the centroid, right? And I think just to plot the center or plot the centroid of each and every object. What I really need is the bounding box coordinates and width and heights, and I need this region extracted from the original image, right? So these two are what's important to me, right? Then I could have saved this, but I simply chose to show it, right? So this is so it contours external contours 5 so on. So these are what I have cropped out. Right? As you can see, so without real human intervention, it has done a proper job. Right? Okay. Right. So what we can do with the things taught in today's lectures is just this. From here onwards, we need some access to some of the algorithms, some recent developments, and so on. Right? But essentially, this is kind of the maximum stuff that you can do with what we have learned today. Right. So, yeah, so the lecture is kind of over for now. But anyways, let's have a small discussion on. So how can I classify now that I have cropped out the image? I will be able to save it. Right. I have taken a screenshot and save it. But anyway, let's save it to observe how I code. See, I have the images over here, right? Now let's take this image for example. So what can I do in order to figure out what's called, let's say I'm a blind person. So I'm a blind person, but somehow I can code. But I need to know what this image is. So what's the next step? What can I do in order to figure out what this is? So it's a camera, right? So what techniques can I use? I'm just kind of having this informal discussion, figure out what kind of things you know and how your technology awareness is. I think I haven't gone through this, but you will be able to, I think you are to tell me, right? So what can you do to figure out what this is or figure out what this is? Yeah, that's why. Of course, we have some classifiers, so there will be multiple classifiers out there. All the front of neural net CNN based classifiers are out there, right? But the issue is, will the pre-trained or will the existing CNNs have the camel as one of their parts? Right? So, in about this existing CNN is the fact that you can classify it as long as it's trained on that particular class. For example, the pre-trained or the ADA competition neural networks, so they have 80 classes that they are trained on. So I don't think the camel is within the big classes. That might be a issue. So anyhow, that will have. So one easiest option that we can do is run a CNN based classifier if it's trained, right? So if it's not, we can perhaps someone has trained it on camels and on these objects and whatnot. But anyhow, so we'll use the most, not the most recent, but kind of the most recent or the kind of a hot thing in the internet right now. So we'll use a LLM to figure out what this is. So I have cropped out the images and now I already have done it. I haven't done any coding, right? I just used pure English and I gave a system instruction as to provide a short caption for the images that are being provided. Right, so it figured out that this is a camel, and in fact, it went beyond that and it figured out this is a zero test. So, you know what a zero test is kind of something similar to that. And as for the arrow as well, it also figured out that this is an upward pointing arrow, right? Now, I did this particular thing because there are few of you guys who are doing image detections and image classifying stuff, which require a ton of training to do, right? Sangha and Mudita, I know for a fact that you guys are doing it, right? But you cannot do your stuff using the pre-existing or the off-the-shelf YOLO networks that are out there because they are limited to 80 classes. Right? So, but if you can somehow segment out individual objects, you can send these objects programmatically to an LLM. I'm using Gemini in this case. You can send them out programmatically to an LLM and have it figure it out for you, right? So not just for you two guys, but for all the other guys, right? As well. This is where the machine vision world is headed at. Focus on the very basics and focus on the very latest stuff, right? The CNNs in the middle are kind of getting out of fashion. Okay, so yeah, then there's another interesting application, the one which we spend around 10 minutes or so, right? So just 3 seconds. Yep. I didn't even get the system instructions or anyhow. I just wrote figure out the card color, card type, and card number. Right. So it did it quite accurately. You can go home and feed in multiple cards if you want to try to figure out the capabilities of the system. But anyhow, these might have failed when GPT-4V came out back. It was not really that great, but now even the smaller ones are great at doing these kind of things, right? So 10 minutes or so wasted, I think. Not a waste anyhow, but you see where this is at, right? But that's not applicable to every single machine vision case. So definitely what we'll study in the next lecture cannot be solved using these LLMs. Right, but finally I just want to say that what we did with the camel stuff is something that you guys should try out as well. And if you train CNNs on your own, it will simply become a photography project. Right? That's why I didn't take such projects last time as well. So these are usually done by, so I know for a fact that Orel IT or a large arm of Orel IT was related to doing these image annotation stuff. And the guys who work there were people who had simply passed out from A levels and want people to edit cameras. Right? So they all work was to do image annotation, and there were companies in Kenya, most African countries. I think OpenAI trained tons of their stuff using African labor. So they are not really intelligent people. No, I'm not saying they are not educated people. Right? Image annotation can be done by school leavers. Right? So in our work, we should not get to their level. we should try out something new, so we should be updated to the latest stuff and try to incorporate the latest stuff into our workflows instead of kind of going into photography and doing image annotation, right? For now it's okay, but definitely I don't know, a few years time, so these things are growing exponentially, and within few years time, even kids will do this CNN stuff. So yeah, I did this just to kind of encourage you to play around with these VLMs and so, because it would be too late once I get to that stage to begin again. Right. Yeah, and if you want to play with this is Gemini AI Studio, right? Just Google it and you will get the link to that. So at the moment, it's quite great because they only limit us in how many requests we can make per minute and per day. But anyhow, even their pro versions or the latest versions are made available to us for free. But there's a small limitation. We can only send 2 requests per minute to the 1.5 pro version. But anyhow, I haven't paid a single dollar to AI Studio to this date. I actually came here after wasting my time on the OpenAI API. Right? So you can test this out in a GUI, and you can also get the code to run it using Python as. Yeah, and there's a good documentation. You can access. Google will excels at documentation, and there's a link to documentation anywhere. So in the later lectures, I will be going into this in detail, right? But this is something that you can simply work with by yourself. At the moment, there are no YouTube videos, right? Because it's a kind of a new thing, and mostly because it's a very intuitive thing. There are no YouTube videos, maybe one or two, but anyhow, almost zero. So I suggest that you get working on it right now. At least to check out what it is. Right. Okay. So that would be it for today. I will upload the lecture and I will upload a take-home assignment as well. So get working on that once I. Right. You all can leave now. Uh, have submit a recording.